All right, we're now in chapter 12, where we're going to continue finding derivatives, but instead of doing it the long way, the limit as h approaches 0 of f of x plus h minus f of x all over h, there has to be an easier way, right? Because what happens when our functions get a little more complex? Well, then doing that long limit definition is going to be really hard. So let's first start off by doing these few problems. I think you have this at the top of your notes, right? What if I gave you these few problems and I asked you to find the derivative? Well, if all we know how to do is use our limit definition, then we would have to do that for every single one of these problems. We would have to do the limit as h approaches 0 of f of x plus h, so wherever I see an x, I plugged in an x plus h, minus f of x all over h, right? The x's would cancel, and then I would be left with an h on the top and an h on the bottom. Well, h over h is just 1. Those reduce. And so the limit as h approaches 0, well, since there is no h, I can't really substitute in a 0. And so if my value is 1, it's always going to be a 1. So my derivative would be 1. If I was given an x squared function and I was asked to find the derivative, well, then I'd have to do the limit as h approaches 0 of f of x plus h minus f of x all over h. Pause the video, FOIL, combine your like terms, do the whole process. So as I FOILed and I combined my like terms, I had an x squared minus x squared that canceled. The terms on the numerator that were left had h's, so I could GCF out an h and reduce it. When I do that, I ended up with a 2x plus h. And then I can apply the limit as h approaches 0, squish those 2 points together, and I end up getting the derivative of 2x. Okay, what about c and d? All ratio. Find the derivative. Go. The limit as h approaches 0 of f of x plus h minus f of x all over h. What this means that I would have to do then is take this x plus h times another x plus h times another x plus h and FOIL them all out. Combine like terms. Not make any mistakes, factor out an h, reduce, and so on, right? Okay, pause for that for a second. What about d? What if I asked you to do the derivative, find the derivative of x to the 7th? Well, if all we knew how to do was that long limit definition, our setup would look something like this, right? And then what would this mean that we would have to do? Holy crap, we'd have to do that x plus h times another x plus h times another x plus h. You'd have to FOIL it out 7 different times. That would take forever. I'm pretty sure I would make a mistake somewhere along the line, and it would get really ugly really quickly, right? Well, if we fast forwarded and found the derivative of both of these, the derivative of x cubed is really 3x squared. And the derivative of x to the 7th, if you were to work it all out, would have been 7x to the 6th. So is there a pattern or something that you noticed where we can take the derivative more quickly, more efficiently than doing that limit as h approaches 0 definition? You might have already seen it in a different class, or you might have noticed the pattern already as we're doing more and more of these. Well, there is a rule that we have and we can use to find the derivative a little more quickly. There is one other one that I didn't notice, but if I have the function f of x equals 3, well, the derivative of 3 is really 0. So let's go ahead in the next few videos talk about the different rules we have to find derivatives more quickly instead of doing the limit definition. Now, we still can use the limit definition, and actually these rules that we're going to learn come from the limit definition. There's actually proofs in your book that use the limit definition to prove these rules, but what we're going to do is we're going to learn a bunch of different rules to help us find derivatives of all different types of functions a little more efficiently than using the limit definition.